Oh man. I'm just getting us back to 323. They're going really well. The projects look really good. They're all like really interesting kind of projects. Oh, let me get this up. Turn off the echo. All right. So I did not get another video put up from yesterday. There was one on Tuesday, but not yesterday. So now we're behind schedule. How is homework 3 going overall? Where's like what's the awesome points? What the heck is going on, and then the meh points. Those are good. All right. So the first couple of parts, like setting up, understanding vectors, were kind of like golden. A lot of that is probably review, like probably brushing off some cobwebs, but mostly just finding components of vectors. Then 323 we started last Friday. Now we're back in the classroom. That was that pendulum on a spring. How does that one feel? Like, no? No? Let's see. We'll open up Tuesday's notes. Discard that. Like, kind of the 3-step process, really, like, I think of it as 2 steps, but step 0 is sort of like before you even start the problem, just thinking about what's involved in the problem. When you have like the spring, so in this case we have like a spring and then something that's moving around connected to the spring. When I'm thinking about that moving, I have to know, all right, there's 2 degrees of freedom. So in order to know where it is, I either need to know like an X and a Y, theta and R. So that's like step 0, is that if I know that there's 2 degrees of freedom, I'm looking for 2 equations of motion. So 2 differential equations that are describing acceleration in terms of position. And it's okay if they're all coupled and weird looking, but I need 2 of them. That's the main point. And then the next step is like build that free body diagram, set it equal to that changes in momentum, and then I can put all those vector components into like the equations that I need to solve. That's kind of that 2-step with an extra step 0. Because I like Python. Python's all 0 based. So step 0 is like the baseline. So if you can get through like this part, like understanding why it has 2 degrees of freedom, that's great. And then if you can draw that free body diagram, awesome. From there, looking at the components, sometimes that gets a little tricky of like what's parallel to what, especially in this case when we're using radial and transverse, like an R and theta components rather than typical X and Y. But you can use X and Y. You'll still get you'll still get those two equations of motion. They'll just look a little bit different. Like all the sines and cosines are in different spots. So if you can get there somehow, then you'll have equations of motion, and then that's good. Then everything after that is kind of like a murky, like check in with an applied mathematician on like how do I get rid of this sine, cosine, how do I get rid of a cosine? All that's like bonus work, I guess. This is like a broad, I don't know exactly what was murky, but my guess is kind of like what is the point of all of this is usually the first question people have when they're looking at you, like throw a whole bunch of equations up on a board. I don't know, were there specific points that you were like yeah.
Surprising the entire equation. Usually when I do something like this, we're given it in like Cartesian or something like that, and we're just translating.
And then like go from one to the other?
Yeah.
So at least for me, I think that these couple of steps of like going from understanding how much motion you're trying to model to the point of like, okay, this is the equation that describes my motion. I think that's the most important part of this class. Everything else is kind of like extra applied math and like engineering. Sometimes it's numerical methods, like you want to plug it into computer models and stuff. But for me, I think if you can do this for any situation, then you're leaps and bounds above a lot of engineers that they might have like a lot of good like math and problem solving skills. They can plug in numbers, but this is a very hard thing to do of like, how do I make the problem so simple that I can actually turn it into an equation? And it's a hard skill to have because you want it to be complicated enough that it describes what you want to describe, but simple enough that it's not just like waving your hands of like, well, it's super complicated. It's like, well, is it? Or are you making it super complicated? Yeah. So and we could try another one, because the next one is also kind of looking at like what are the forces involved? So how many degrees of freedom do we have? How many forces, what forces are there? And then find some equations to describe acceleration. So we could try it again on the next problem, see how that goes. Maybe we'll finish today. If we don't, it's all right. We can bump it off. I keep pushing things back, but sooner or later the semester will end, right? Like, oh no, time, it's a harsh mistress. It is going by too fast. It's too much fun is the problem. It is. Okay, so we have this problem of a lunar rover traveling constant speed over a semicircular hill. We're calling it semicircular, but really, so like constant radius of curvature along this hill. Same as like driving over Horse Barn Hill, something like that. So we're driving over the hill, and then we know acceleration of gravity is like 1/6? 1/5? Something like that. I think about 1/5. So how fast can we drive this rover over the hill without leaving the hill? So we're not trying to like die hard our way off the hill. Yeah. What? It would be more fun. Yeah. So remember our 3 steps. Let me give myself a little bit. All right, so the first step that we need to understand is for this rover to understand how fast we're going, how many degrees of freedom do we need to give it?
2.
2? We need 2? Yeah. What would be our 2 kind of degrees of freedom? Oh, no, go ahead. Or
There's 2 X and Y.
we could call it X and Y, so we could say that there's some kind of like X and Y, so 2 degrees. What were you thinking? Same thing, like R, okay. It's going like over a hill. So a lot of times if things are circular, we can get it into a Cartesian coordinate system. Like this is what computers do. No matter how circular your problem is, it jams it into a Cartesian coordinate system and then solves everything that way. But it's for us, you'll end up doing more math. So you're taking a round problem and jamming it into a square system. It'll work. You just need a big math hammer to do it.
Yep, R and theta would be better.
So we could use R theta, something. Are there constraints? Yeah.
If we use R theta, don't we then get 3 degrees of freedom? Because
Why?
R is a function of X and Y.
R is a function of X and Y, but it's dependent, right?
Yeah.
So it's so we could say like X is R cosine theta and Y is R sine theta. So whether I choose X and I could choose like X and R, kind of a weird thing to do, but it would still work. And I would have like 2 independent measurements. One is like distance from something, another one is like an X direction. They're not like independent of each other. They're not orthogonal, but it would work. So as long as I have 2 independent measures of where that thing is. Do I have any constraints on the motion? Yeah? What's one constraint?
You only have half
Half
the circle.
a circle? So that's describing like range of motion. So that's like it bounds. So like one thing I could say is that there's a certain bound on the angle, that the angle can only be a certain range, but it's still a degree of freedom. Like it's still free to move to any angle. It's just it can't move to like negative 180. You can't be driving upside down on the hill. So that one gives like range, but it doesn't delete, it doesn't remove, it doesn't create constraint. Are there constraints though? Is there? Yeah.
Does R has to be a upper degree?
So R is a fixed value. R is fixed. So if I say that this, if I'm describing it with R and theta, but R is 100, do I still have 2 degrees of freedom? Just 1. Because every time I add a constraint, I remove 1 degree of freedom. Yeah.
Isn't it gravity?
So gravity gives us another force. So yeah, and sometimes that feels like a constraint because it's like, well, the kinematic equations are directly constraining my motion, but really that is a solution to a problem that has like 1 degree of freedom. So gravity we treat it as a force, so it's part of our free body diagram, but not like a constraint on our kinematic diagram, except for free fall, where ma equals mg, and so a equals g. But a lot of times it's kind of like MA equals G plus the normal force minus something else, something like that. Yeah. Do I have other constraints? Yeah. Ooh, constant speed. Yeah.
I guess it'd be 16 times 12.
16. What is 16?
The massive velocity.
Oh, how fast it's moving?
Meters.
You're jumping ahead, just solving it. So, well, first off, I want to jump into, if I have a constraint on radius and a constraint on speed, and I only had 2 degrees of freedom, how many do I have now? I have 0 as far as like a differential equation. I should not have a differential equation of saying like theta double dot equals something, because theta double dot is 0 already. So theta dot is, we'll call it like V over R, right? Like some R theta dot is V, so then theta dot is some fixed value. Yeah.
The A squared equals V over R.
And then A squared.
A equals V squared over R.
A is V squared over R. Sometimes, yeah. If V is constant, and here V is constant. Yep. So actually, we started off with 2 degrees of freedom, and that was a great like thought process of starting off with the fact that, look, we're moving in 2 dimensions, but what do I know about the motion? I know it's on a fixed curve, so that means I remove that one of the constraints, and then I know that it's moving at a constant speed, so I remove a whole nother one. So now I'm not solving a differential equation. I should be able to set forces equal to something and end up with like just numbers where this force is causing that motion, something like that. Back to like what we did in module 2. We knew what the motion was and we could solve for the forces involved. Cool? All right, so now, what are the forces? How do we draw that? Oh, yeah.
Gravity.
Gravity, all right. Sweet. And that's it.
Normal.
And normal force, how do you want to draw that one? Straight up? Straight up. We can do that. That works. Does it matter if it's on going up the hill versus down the hill? Is normal force straight up?
Change.
It'll change a little bit, right? Yeah. 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 Does it? Which is a good, I don't know if you're like thinking like it's not worth it, or like you're thinking ahead of like it's not gonna be worth it. All right, so what's our kinetic diagram? Where's it going? Around, yeah, some kind of circle. What is how much acceleration? So it's not changing speed. So
Acceleration is due to gravity.
this like MA whatever, I can call this like the amount that it's changing its speed has to be 0. That's like the tangential acceleration. Yeah.
But you still need a force applied.
Some kind of force applied.
Yeah.
To say that it's getting up and over.
Yeah.
Yeah, we could say that there's something getting it to keep a constant velocity, right? Like something to get it up the hill, something to get it down the hill. And we could solve for that. We could figure out like how much work is the motor doing to maintain constant speed. I like that. Yeah.
Is it also like, is there friction here?
There is friction. Drag is since there's no air, then there's on the moon. Moon doesn't have air, right? No air, right? No atmosphere. There's dust, but I think it all just sort of settles. there's definitely rolling resistance. Like it's all just sandy rocks. It's like driving on the beach, like a dusty beach. So there would be like rolling resistance, but overall that force applied would have to overcome whatever resistance there is, and so there's something that overcomes what we're moving forward. So is that it? We just have MA is 0, so mg equals n, force applied 0 because it's just something else.
Acceleration would have to do gravity for it to not fly on.
Okay, so there's something else involved, right?
A would have to be G.
A is G.
A would have to be G.
Okay.
Or else it like
So how do we find where's A pointing though?
down.
Down.
Depends where you are.
On the semicircle. Okay. Well, right now we're drawing like at the top.
Yeah.
So let's say we're our moon rover. Yeah, they're always happy. They're on the moon. Gravity's low. Things are good. Life is good. No homework. It's good. So we're at the top of the hill. What is that acceleration down? Well, we know that we can say that it's like mg, but there's also n opposing it, right? So the normal force is opposing it. So how do we describe? And it's not. There's no radial acceleration down, right? Like it's not decreasing r. At least if I call this. Yeah, theta that way. So the radius is that constant radius going up and over the hill. So there's got to be something. What's opposing? Yeah.
Did I mention friction yet?
Friction? Do you think friction keeps it on the ground though?
I guess it doesn't keep it on the ground. I guess it's another opposing force.
Yeah. So friction's our main friend for driving because it's the only thing pushing us forward. And then the thing that does resist us is called rolling resistance, which looks exactly the same. Like the equation is still mu times n. It's just the mu. It's not like sliding friction. It's a rolling resistance. Describing here it'd be like because it's deforming the sand and it has a certain radius. So bigger radius, less resistance. Smaller, more. Yeah. But force applied, we kind of like lumped it all into force applied, the total. Something maintains speed, but we don't know what it is.
Centripetal acceleration equals a set.
Ooh, some kind of centripetal acceleration, right? Because we're moving on a curve.
Yeah.
So we need something telling us that m times that like centripetal acceleration, because we're moving along that curve, that's what gravity is trying to hold us on the curve. Normal force is not helping anybody. It's like trying to push us off of the curve. Cool. What is centripetal acceleration? What is that one? That v squared over r. Yeah. So we have 0 equations of motion, but we do have like some kind of like static equations, right? Like almost like statics. Everything's moving, so technically still dynamics, but not. Sorry?
Is it really moving?
Is it moving? I guess if you're moving the same speed, it would also look like it's not moving. Is that like everything's relative?
Motion is relative.
Yeah, motion is relative.
Especially if we have this position.
So here, in the radial direction, I could say that this is like m v squared over r. Really, it's like a negative, right? In the theta direction, it's all equal to 0. So what forces are along which parts? Like which one is along ER? Which one is E theta? What force goes where? Yeah.
Would the force applied be theta and then the normal force is going to be on?
Yeah, so we could call this one, at least in this case, we could just say that that's force applied. So that whatever, so when it's at the top of the hill, you don't need any force. If you were already moving at a certain speed, you don't need to keep applying a force to maintain that speed. So that's all that one's saying. Nice. And then everything else, plug it in here. And minus mg. Cool. So if we do want to die hard and fly off the hill, what do we need? What do we need to happen? When does that occur? What? Force greater than mv, right? Than gravity. Yeah. When normal force is 0. Yeah. So if normal force is 0, then we're moving so fast that it's no longer. It can't apply a negative force. There's no like magnetic normal force here. Just dust, sand. So like when n is less than or equal to 0, then our guy is like, oh, you know, like flying off, getting some air. And I can kind of rearrange things and say, depending on how fast I'm going, then this is my normal force. So I need it to be more than 0. What was the number you came up with?
1612.
What do we think? What are some other numbers that people come up with? Does mass matter? Do we know how heavy it is? 200. Okay. Is it going to change if it was like 400 kilogram? No? Not really, right? I think R is 100. Yeah, 100 and G is 1.6. 12.65. We got 2 of those. Or I guess. Say 2 checks, 1 check here. So at least like if I'm trying to solve this, I would say n is that g, well, like n over m, v squared over r. All of that is less than or equal to 0. So 1.6 minus v squared over 100. Oh. So then add v squared to both sides. So v squared is more than, if v squared is more than or equal to 160, then like launching off of this hill. Make sense? Is that what other people, is that the 12.65 or is that 16? 12, yeah, about 13. Yeah, works out. And technically, if I'm moving left or right, same speed. That's my like upper limit on how fast I can go. Coming back for a second. If this is rotated a little bit, like if I'm coming up the hill versus down the hill, does that matter? Like here we solve for the very top of the hill. Is that the worst case scenario or the best case scenario? Best case? Like when you're going back down, you expect different condition? What do we think? So mg is still going to be down. And whatever force applied we had is going to be pointing like up like that again. And then this is kind of like mg, that theta is right in that internal angle there. And then which one did we need? All we needed was that radial term, right? So it's still like a positive n. So n is at least the way that we kind of set up our problem. We did a little bit of extra work up front, but we figured out n is always along that radial part. Yeah.
And approaching 0 when you get towards the left or right hand side.
Oh, if you're,
Yeah, like if you're like here,
yeah.
and approaching 0.
All right. This comes up here and there too. If we extend this hill down to, or like when you're climbing the hill. How many hills extend to 90 degrees? Many? So think about it. Here's another question. If the angle, if I think of the top of the hill as angle 0, and I start walking down the hill, so constant radius, I'm walking down, so think about Horse Barn Hill. At the very top of the hill, you're at angle 0. Now walk down to the bottom of the constant curvature. The more you walk away, the bigger the angle is getting. So if I walk to a point where I'm 90 degrees off of the top of the hill, then the slope is 90 degrees. And I think we talked about this before, like that's terrifying Like if you saw, it would no longer be a hill, that would be a straight up mountain if it had like an actual dome. So when we say the curvature is constant, it's like, well, we're engineers. Like it's constant for a while, yeah, for a little bit. So maybe we have like plus minus 10 degrees, something like that. But you're right. Like if we were coming out a hill and it was actually like start at 90 degrees, go up to 0, then back down to negative 90. I mean, I think the poor rover would just, it'd be slamming into a wall and then somehow climbing, maybe climbing, I don't know, probably just, that would be the end of the rover. So anyway, really we've got like something like this, like some kind of smooth transition, 20, maybe 20 degrees, like a 20-degree slope is pretty steep. It's the moon, maybe it's extreme. I don't know.
Still reduce our normal force though, correct?
But it's reducing, like normal force is still changing, right? Yeah. So now, instead of an mg, just like minus mg, we have minus mg cosine or sine. It's one of those, right? Cosine part. So do we need a different speed for every angle? Yeah, maybe. What's the, if we back up, as engineers, I'll come back to it in a second, but engineers, we love to like simplify, just take linear approximations of functions, and you'll learn to love it too. Someday, be like, linear functions, these are so fun. So what's linear approximation for cosine theta? I backed up to, this was like Tuesday, I was just, what? It's 1, yeah. So the first order approximation of cosine theta is just, it's equal to 1 for all time. So put a 1 back in there and say this is an exact solution for small angles. Nice. Yeah, small angles are great. We love small angles. Yeah, how small? That is a good question.
We just write assume small angle approximation for that.
Yeah, I do that all the time. I'm just like assume small angles. And
For this problem though, we can assume small angle approximation.
Yeah. You can assume, because when we drew everything at the top of the hill, really what we were doing was implicitly assuming theta is much less than 1, that it's a really small theta. So cosine of theta is 1. Yeah, if you want to know like how small is small enough, you can take theta squared over 2 and see how big that is. And that's the error, because cosine theta is 1 minus theta squared over 2 plus theta to the 4 over 4 factorial, and then minus, yeah. So if we say like, all right, theta is going to be 0.1, 0.1 squared over 2, 0.01, so 0.005, good enough. If theta is 1, like actual 1 radian, I always forget how many degrees that is, but 1 radian is 1/3 of 180, so 60 degrees, around 60 degrees. So if it's 60, now we're talking our error is 1/2 for cosine theta. It's getting bigger, but maybe it's close enough. Cool. Through 34, 37. That's a lot to do in like 5 minutes. 34, 37. Yeah, we're not going to get. All right, but we can knock this one out though. And I think that's all we need for this one. So this one, there's A, B, C, D, E, or A, B, C, D, E, but for the most part, we're just trying to find how many degrees of freedom do we have? What's the free body diagram, kinetic diagram, and then what is the equation of motion? So the buoyancy force is 2 mg. Force of gravity is mg. So for a balloon on a string, the string is taut, so it's well learned. It's been taught. So it's all stretched, so constant length. Yeah.
Do we have any degrees of freedom?
Do we have any? Maybe, maybe not. No degrees. Yeah. Okay. 1 vote for 0 degrees of freedom, just like the last problem. 1 degree of freedom. Maybe 1. In the last problem, you went through a great thought process, like as a group of like, all right, let's start off with 2, and then what are the constraints on that? So we could start there. We could say there's 2 degrees of freedom because we need to know where the balloon is. So we need an X and a Y coordinate. Are there any constraints on X or Y or R or theta? Yeah.
The radius.
Yeah, that the radius is a fixed radius as long as the balloon's not like the string's not all curled up because it's in tension. So we have one constraint on those 2 degrees of freedom. Do we have any others? Like any constraint on how the balloon is going to bob back and forth? Not really, right? We just know it's going to be some angle, and yeah.
Like the gravity and the buoyant force?
So forces tell us how like the equations of motion will play out, but they don't change like the constraints on its motion. And that's a really weird concept to think about because the force does absolutely changes motion. Like when you apply force, that creates acceleration, but it doesn't create a constraint on acceleration. It's giving you an equation to say that acceleration is now F over m from that force. And yeah, and usually people kind of struggle with that, with like that spring and pendulum. It's like, well, the spring is there. Isn't that a constraint? It's like, no, that's a force. Forces are not constraints. Yeah. So it's something that you're supposed to struggle with in this endeavor. And you'll come out stronger on the other side, forged in confusion, making chrysalis. All right, 1 degree of freedom, 1 equation of motion. That's all we need is 1 equation of motion. Because degrees of freedom equals EOMs. All right, what forces? How do you want to draw the forces on here?
G going downward.
Okay. I'm going to put another one. Yeah.
Wouldn't it just always just stay straight up?
No, it's kind of like a spring or a pendulum, right? Yeah, a spring or a pendulum. Like if you give it an initial angle, then it's gonna bounce back and forth between those two angles, unless we include like damping to say like there's something slowing it down and causing it to.
Our FB is twice as great as our FG.
Where does FB point? Where do we put that one? Straight up, right? Are we done? No more force? We could put drag, yeah. We only have like 3 minutes left, so I'm not going to put drag in there. Yeah. Yeah, 5 minutes, then we can do drag. Tension along wherever the cord is. So wherever that cord is attached to, there's got to be some tension maintaining that constraint. And that's the other side of like a constraint. Like if you have a constraint, there's some kind of constraint force. There's always, like if you say this thing can't move, something's preventing it from moving, some kind of reaction force. So we'll call that like T, or whatever you want to call it. Cord, C for cord, or S for string, yeah. What's the applied force? Oh yeah, if we wanted to say like something's blowing it, or
because you have a tension on the angle, you need and your total force would be another force counteracting.
well, if we have one equation of motion, then our forces don't have to add up to 0. And even in the last problem, like our forces didn't add up to 0, they added up to centripetal acceleration. Yeah, so there might be an applied force, but at least at face value, if we're just trying to figure out how is this thing gonna move, what's like the general equation of motion, all we need is buoyancy, gravity, tension. And then we can go from there. You can always make it more complicated, but the goal is as simple as possible without any simpler. All right, so then I'm gonna draw in kinetic diagram. So along that tension, it's kind of like my MAR, that radial acceleration. That one has to be 0 because it's not accelerating away. And I'm drawing this because I like to maintain theta, E theta in the same direction, always off of the x-axis, always off of like my theta equals 0 line. So then 90 degrees to that AR is A theta term. Do I want to say, it's not really equal to 0. It's not really fair to say. R double dot is 0. I'm writing those two cylindrical coordinate acceleration definitions. It's always the same definition. You can derive it, you can look it up. It's always these 4 terms, 2 in the radial, 2 in the theta direction. Like describing rotation. But we know this one's 0, and we know that one's 0. All right, what forces are in these two directions? We only have a minute. Well, we have negative 10 seconds, yeah. This is what I get. I'm just throwing it in there real quick. Oh man, and I was gonna say we'll come back on Monday, but Monday's the last day of the senior design. This thing's really throwing a wrench into our schedule. So Wednesday. All right, I'll rearrange our schedule and we'll figure this out. Have a great weekend. Thanks so much for joining back in person. And we'll be back on Wednesday for classroom. I'll move homework. It's not due today because we didn't even finish it. So thanks, you too.